Hello everyone, welcome to my YouTube channel. Today I'm solving Leetcode question 787, cheapest flight with K-stops. So there is a one fun fact. Have you noticed the 787? Try search 787 cheapest flights on Google and see what you find. There are n cities connected by some number of flights. You are given an array of flights, where flights I equals from I to I, price I, indicates that there is a flight from city from to city to with the cost of price. You are also given three integers, source, destination, and k. Return the cheapest price from source to destination with at most k stops. If there is no such route, return -1. So let's try to first understand the problem. So there's flight from source to destination, and then there could be many connections and many stops in between, but they fixed the maximum number of stops at k. At most k stops means k plus 1 flight legs. So what does that mean? So let's say from 1, in this example, from 1 travel to node 3. So there is a one stop in between. If you don't want to take the direct flight, you can go from 1 to 2 and from 2 to 3. In this case, if you go to 2 from 1 and then go to 3 from 2, so you will see there is actually one stop, so k equal to 1. And then there are k plus 1. There are two flight legs, so flight from 1 to 2 and then the other flight from 2 to 3. So at most k stops, at most. So what if, let's say, we have k equals 1, but then the cheapest way to reach the destination is through the direct flight. In that case, you can just go for it. You can just take one flight, directly travel from source to the destination. So in that case, the number of stops you are in your route designed is 0, which is less than k, which is perfectly fine because the constraint specifies at most k stops. So what's the idea for solving it? So before diving into the idea, let's go over this example 1. So in this example 1, so we have a list of flights. So flights indicate, let's say 0 to 1 costs 100, 1 to 2 costs 100, 2 to 0 costs 100 as well. And then 1 to 3 costs 600, 2 to 3 costs 200. The source node is 0, destination node is 3, and then at most one stop, k equals 1. So you need to travel from node 0 to node 3, and then with at most one stops. So the output is 700. That's it. It's the cheapest ticket price. So you need to take this right path from 0 to 1 and then from 1 to 3. So the total cost is 700. Is there a cheaper path? Yes. So you can travel from 0 to 1, 1 to 2, and 2 to 3. In that case, the total cost would just be 400. However, this cheaper path has two stops, so which does not satisfy our constraint k equals 1. So that's why our output for this example is 700. So for the second example, so 0 to 1, 100, 1 to 2, 100, 0 to 2 cost 500. The source node is 0, destination node is 2, and then k equals 1. So there are two ways actually to go. One way is to take the direct flight from 0 to 2, and it costs 500. The other option is connect at node 1. In that case, you have one stop, satisfy our constraint k equals 1, at most one stop. So you travel from 0 to 1, 1 to 2, the total cost is 100 plus 100, 200. So compare those two possible routes to travel from 0 to 1, to travel from 0 to 2. The cheapest one is the one with connection at node 1, with the output is 200. So let's say it's still the same network, but in this time, we change our constraint. We still travel from node 0 to 2, but at most 0 stops. So it forces us to take the direct flight. So in that case, the output is 500 because we cannot go for the cheaper route that's connected at node 1. since it does not satisfy our constraint k equals 0. Okay, cool. So now let's talk about the idea to solve it. So it's actually a popular algorithm, bellman-ford algorithm. This is another shortest path algorithm, and then it can also handle the negative weights. So the most popular shortest path algorithm is what we talked before, the Dijkstra shortest path algorithm. So this one, the bellman-ford, is the algorithm that can be applied to this problem. So I would say if you know this algorithm before, this problem will be super easy to solve. But if you don't know that, it will be hard to actually come up with this algorithm. The reason why we are utilizing this one to solve instead of Dijkstra shortest path algorithm, you can try the Dijkstra shortest path, or you can try the BFS with some tweaks, but those algorithms will result in the TLE, the time limit exceed for this problem. So let me describe the overall idea. So basically you iterate through k plus 1 times. Remember we said there's k plus 1 flat legs. In each iteration, represent one flat leg. For each iteration, calculate the cheapest price reaching each city based on the cheapest price from the previous iteration. So let's say in the previous iteration, you can reach the destination 1 and destination 2. And then now you can, in the current iteration, you can calculate the cheapest price reaching each city based on the cheapest price from the previous iteration. However, let's say if in your previous iteration, you cannot reach the node 3. Let's say node 3 has not been reached in all previous iterations. So in this current iteration, we shouldn't consider the flight from node 3 to any other nodes. Why? Because this node 3 hasn't been reached by flight in previous iterations. So we keep two data structure. We have a list called current. Current I is the cheapest price to reach city I after current iteration. So basically this is what you are updating your current iteration. List previous I is the cheapest price to reach city I after previous iteration. Basically the starting state. So when you are calculating the current state, you are referring to the previous state. So the time complexity is overall O edge times k, and E is the number of edges. So here is the length of the flights. So you have a flights. Remember, you have a flights array, and then the space complexity is actually O 2 times n is On. We are utilizing two additional data structure, current and previous. So let's start coding. So we initialize our previous. Previous equals the float infinity times n. And then at the very beginning, because you can reach the source node, let's say our flight start from the source node. So in that case, we assume that the source node is already reached. What's the cost of travel from source node to source node itself? It's absolutely 0. And then we can check and loop through the flights. So before that, let's try to loop through the k plus 1. So in this case, each iteration represents one flat leg. So in that case, we force at most k stops, aka at most k plus 1 flat legs in the route we are constructing. And then in each iteration, we create a current. So we first initialize it to the copy of the previous. And then we are trying to iterate through the flight. Source, guest, from, for origin, destination, and then also cost in flights. In that case, I'm update the destination based on origin. Let's say if this origin has already been reached in the previous flight. So in that case, which means let's say if this origin node has already been reached in previous iterations, then the cost to reach this node wouldn't be the infinity. So in that case, we updated uh, the the cost for reaching the destination. Okay, after iteration, after we finish updating the current state, in this case, we just uh, reassign the previous state to the current state. Reassign the current state to the previous state. Why? Because the current state becomes the previous state going into the next iteration. And then let's see if we can find it. So if we can find one, in that case, the previous dust is not float infinity. In that case, you can reach it. So in that case, you just return previous dst. Otherwise, you just return previous return -1. So let's run this code. Oh, my bad. I made a mistake in the variable name. Oh, return -1. So this is our solution. So, okay, you may be wondering why we actually need the previous and current state. Can we just like create one list current and then just make updates based on the current? Let me show you one example why we need both to modify the uh, previous and current instead of just utilizing one additional list and modify current in place. Let's say utilizing previous and current, you initialize everything at the infinity. And then the cost from source to source is always 0. In this case, let's assume we start at node 0. That's our source. So SRC equals 0. I mean, it could be any other number. So here we just illustrated as an example. So the cost from source to source always 0. And then we know at the very beginning we can reach this source because that's our starting point. So in that case, we replace the infinity with 0. So in the first iteration, we look at the all the possible flights. So we only care about the flights that are starting from the source node because we can only reach the source in the previous iteration. We haven't reached any other nodes yet, so we only consider the flight legs that originated from this source node. So in that case, that's the flight from the source node to node 0 to node 1, and then the cost is 100. So in this case, we update the current to be 100. And then our previous state, the list is still the, the list on line 59. In the second iteration, you are looking at, okay, so in this case, in the previous iteration, we already reached the node 0, node 1, so we can check the flights from node 0 or the flights from the node 1. So in that case, there is a flight from these two nodes to the node 2 and then node 3 as well. So we update their cost. And then in the third iteration, we just find the slightly better node, better flights with a lower cost. So that's kind of how I update. So you know like how they get updated in each iteration. So what if we just utilize current list and only modify in place? You just make it super hard to track the number of stops. So let's say in the first iteration, because you are updating the current list at the same time, so in that case, so you just like keep updating like and then until you get all the cost. So in that case, it's hard to track and satisfy the number of stop constraints. So that's why we need to track the previous state and the current state. So for the current state, when we are trying to update the current state, we only update those flights that's starting from a node that's already been reached in the previous state. So this is the end of my video. If you like my video, please subscribe to my YouTube channel. That would help a lot. Thank you.